Hi, in this video we will see how a function can fail to be differentiable at a point. In particular, we will discuss the relation between continuity and differentiability. Okay, let us start with a very important theorem which says what is the relation between these two notions that we have studied so far, continuity and differentiability. It says if a function is differentiable at a point A, then it is continuous at A. Well, it means that, differentiability is stronger than continuity. Okay, and how does the proof goes in this case? So see, to prove that f is continuous at A, we need to prove that limit of f of x as x approaches to A is f, the value of f at A. Or equivalently, we can show that the limit of f of x minus the constant, which is the value of the function at A, as x approaches to A, this is equal to 0. Well, how do we show this? Well, let us just write this, limit of f of x minus f of A as x approaches to A. Well, we know that this limit appears, this function appears in the numerator of the average rate of change, which when you let x go to A, that will give us the derivative. So I will then generate that ratio of the differences. Since I divided the whole thing by x minus A, I can multiply it by x minus A also. Okay? Then, you see this two piece here, up to here. This one and this one. These are product of two functions which have a limit as x approaches to A. So we can use the product law and write it as x goes to A, x goes to A. Product of the limits, yes. Well, the first piece, why did I say this limit exists? Because we assume that the function is differentiable at A. So this means that this limit exists, and we denote it by f prime of A. How about this one? X minus A, as x approaches to A, is A minus A, which is, 0. And 0 times anything is 0. So we showed that if function is continuous at a point, then it's definitely, if it is differentiable at a point, it's definitely continuous at that point. Okay, so the remark, something that you may think of, this statement says that a differentiability implies continuity. Is the other way around true also? Are all continuous functions at a point differentiable at that point? Well, the answer to this question is no. So the inverse of the theorem is not true. And indeed, you can find an example which is continuous at a point, but it's not differentiable. You know that example. And we have functions which are continuous at any point, but not differentiable. You have to be able to give that example right now, because we have worked about these examples. And well, this is absolute value of x is continuous at 0, but not differentiable. So that's a very good example of continuous function but not differentiable. All differentiable functions are going to be continuous, but not the other way around. The second remark is that we can use a version of this theorem which makes sense more, maybe, if something is not continuous at a point. So the equivalent version of the theorem is if f is not continuous at a point A, then f is not differentiable at A. Well, this gives us the first class of the functions which are not differentiable. So if I want to make a list, how does differentiability fail? So the first case will be discontinuous functions. If a function is not differentiable, is not continuous, it's not going to be differentiable. So this includes a function is not defined at A, so if you look at the graph of those functions, it will be something like this, not defined. Or it is defined, the limit does not exist. Something like, well, left limit is not equal to right limit, or something, you know, the oscillatory case which the limit does not exist at those cases, something like sine of 1 over x, something like that. Or, well, one side limit exists, the other one doesn't, and all these things. So all these cases, these are not differentiable. And as we saw above, this is not the only case. There are other cases which are not differentiable. Graphically, these guys are the ones that have corner, or some people say cusp, all these things. But the limit in these cases are the limit f of x minus f of a over x minus a as x approaches a does not exist because its one-sided versions are not equal. Are not equal. So these guys are the ones like, okay, absolute value of x. You see, when you go from the left, the limit f of x minus a will be -1. So limit of f of x minus f of a as x minus a. This is -1. If you go the other way around, it is +1. Limit of f of x minus f of a x minus a as x approaches to a plus is +1. Or they are positive infinity, for example, both of them. So something like this also will work. So this is a little bit different than just the two-sided limits are not equal. So when you go this way, this is negative infinity and then comes up positive infinity. At this point, we don't have any continuity. So this was the second case. The third case is also an interesting case. When this is the only case that a tangent line exists, but the slope of the tangent line is infinity. So this is, let me write it, vertical tangent line. So what happens in these cases? So the tangent line exists, but the slope of the tangent line, which is the limit, is plus infinity or minus infinity. So limit of f of x minus f of a over x minus a as x approaches to a. Very special cases, not always. In these cases are plus infinity. So the tangent line exists, but it has undefined slope. So undefined slope. Well, this list can be completed, but just geometrically you need to know the corner or cusp like, vertical, and discontinuous functions, which are the main three cases that a function can be not differentiable at a point.